everyone and welcome to this course on gas turbines and jet engines. Okay. So, today is lecture 22, which is the second lecture of week 5. So, we have seen till now what are the different aspects of real gas turbines, real industrial gas turbines. We have not yet started jet engines. Now, today we will see how to do analysis of or numerical analysis or solve numerical problems for these real gas turbines. Okay. As we have previously discussed, this type of calculations are also called as design point calculation. So, some design parameters, known parameters are given or fixed, specified. Based on that, we want to find out the performance parameters, performance of the engine. Okay. So, let us take up a problem which has multiple of these differences as compared to ideal cycle, and then we will try to see what are the parameters that we obtain and how it is different from ideal cycle. Okay. So, the concept which will be covered. So, we will practice in today's class and in the next class how to solve numerical problems for real gas turbines. Okay. So, I will start by defining the problem by writing the problem. So, we have a gas turbine. We have a gas turbine I have kept a TS diagram because we will need to draw that on that diagrams already to save some time, and the following properties are given. The inlet condition, inlet pressure is 100 kPa, inlet ambient temperature is 300 Kelvin. Okay, let us say that ambient pressure also. Okay, let us so ambient pressure is 100 kPa, ambient temperature is 300 Kelvin. Then we have a pressure ratio R. So, this is a design parameter, remember this is 10. The turbine inlet temperature T max is 1500 Kelvin. Then we also have conversion efficiency equal to, so we will have a conversion efficiency which is equal to 0.98. Then there is regenerator pressure loss. On the air side we have 2%. So, this we can write as delta P regen A to be more accurate. Okay. So, delta P regen A, this is 2% of compressor delivery pressure. Okay. I am just writing 2%, and combustion chamber pressure loss is 4% of inlet pressure, inlet to the combustion chamber, inlet to the combustion chamber. Okay, that is important. And then in the gas side of the regenerator we have a fixed loss which is given as 10 kPa. Okay, so, all these are known parameters. Then we have a regenerator effectiveness of 0.95 and isentropic efficiency of turbine and compressor are also given, and it is equal to 0.9. Okay. So, let us summarize again. Ambient conditions are known, pressure ratio is given, turbine inlet temperature is given. Okay. So, then efficiency of combustion is given, delta P. So, all the pressure losses are given. Then regenerator effectiveness and the isentropic efficiencies of compressor and turbine are given. Along with this, it is also stated that mass flow rate of air through this gas turbine, mass flow rate at the intake is 10 kg per second. sorry, this is not given, we will need to find the mass flow rate. So, we need to find out what is the efficiency, what is the net work output, okay, thermal efficiency, net work output, then specific fuel consumption, SFC. We also want to compare the efficiency, with ideal cycle, and if it is stated that the turbine will generate a power of 50 megawatt, we want to know what is the mass flow rate of air through this turbine, okay, mass flow rate of air through this turbine. So, this also we need to find. So, how to start this problem? So, as you can see, this is a complete design problem which has all the different design parameters and operating parameters mentioned, and we are trying to find the performance of this gas turbine. Okay. So, this is a regenerative type gas turbine with regeneration, but no reheat or intercooling. Okay. So, we again start by drawing all the processes, okay, with the TS diagram. So, that is how we have always we should start solving this problem. Something like this. Then there will be pressure losses, difficult to draw, but we will draw something like this, and on the other side of the regenerator also there will be pressure loss. Now, let us say that compression is from 1 to 2. So, this is 1, this is 2s, this is 2, then let us write 0 1 0 2s, because that we should practice now like this. From 0 2 to 0 3, let us call this as 0 5, which is our standard notation for regeneration. From 0 5 to, let us say, 0 3 is the combustion process, then 0 3 to 0 4 expansion in the turbine. Okay. So, regenerator effectiveness, so this will be slightly lower. This is the point 0.05, that is 0.5 dash, 0.5 dash equal to 0.4, and similarly this is 0.6, okay, which is slightly higher than 0.2. Slightly complex diagram. So, while discussing it, the context will be more clear. Okay, so, 0.1 to 0.2 is the compression process, 0.2 to 0.5, 0.5 has to be lower than 0.4. So, 0.5 is the regeneration air side, then from 5 to 3 is the conversion process, 3 to 4 is the expansion in the turbine, and 4 to 6 is the expansion in the, sorry, not expansion, is the heat exchange process in the regenerator gas side, and 0.6 has to be higher than 0.2. Okay. So, now we start with this problem, and you should note down this diagram while solving, so that you can solve along with me. Okay. So, what we will do is we will start with each state calculation. So, T01 and T02 are the first stage that needs to be calculated. T01 is equal to Ta plus Va square by 2 Cp. In general, this should be the case. Here Va is not given, so there is no ambient velocity, we can ignore. So, T01 equal to Ta in this case, which is already given to us as 300 Kelvin. Okay. This is the inlet temperature, stagnation temperature, which is equal to the ambient temperature in this case. Similarly, P01 also will be in this case equal to Pa, which is equal to 100 kPa. Okay. So, T01 and P01 is fixed, then we go to T02 and P02. So, first how do we get T02? So, we will get first T02s. Okay. So, I have to skip the slide. So, that is why it is better if you have the diagram open, if you draw the diagram. So, T02s by T01, remember T02s from T01 is isentropic process. So, T02s by T01 is equal to R to the power gamma of air, remember now that we are using separate gamma values, gamma of air minus 1 by gamma of air. Okay. So, this is equal to 579, okay, or let us directly write down to save time. T02s is equal to 579. So, I have already done the calculation. So, I am noting down from there, but you should be parallelly doing the calculations along with me and verifying the results. T02s is 579.21 Kelvin. Now, we will use the efficiency definition, isentropic efficiency definition for the compressor. So, we know that eta C is equal to T02s minus T01 by T02 minus T01. Okay. So, eta C now eta C is equal to T02s, which is a known quantity, we have already calculated. T01 is known quantity 300 Kelvin by T02 minus T01. T01 again is a known quantity. So, everything is known here. So, we get from here the value of T02. This comes out to be 610.23 Kelvin. This figure may be familiar if you have gone through the previous lectures, you will see that previously also we have taken similar inputs. We are trying to keep all the problems similar in nature, so that we can directly compare between each of them. Of course, the solution process will be clear to you, and for any other values also you will be able to solve these problems based on this type of approach. Okay. So, 610.23 Kelvin. So, T02 and P02 unknown. P02 of course is equal to R into P01, which is equal to 1000 kPa, because P01 is 100 kPa. So, T02, P02 is known. So, this is from compressor calculation. What next? So, we also have to do calculation for the regeneration process, okay, regeneration process 02 to 05. So, we need to find the inlet temperature to the combustion chamber. So, we need to find the temperature T05, okay. And so, how do we find this T05? So, this is for regenerator. Regenerator air side now we are doing. So, remember that by definition effectiveness equal to T05 minus T02 by T05 dash minus T02, where T05 dash equal to T04. Okay. So, by definition this is the actual temperature rise T05 minus T02 by the ideal temperature rise, which is T05 dash minus T 02, which is equal to T 04 minus T 02. Okay. So, to get T 05 value, we will need to find the value of T 04. Okay. So, first we will need to find the value of T 04. T 04 is the exit temperature at the exit of the turbine. Okay. So, how do we find that? Let us solve for the turbine. So, you can see everything is interconnected in this problem. So, we have to be careful, we have to know, or we have to analyze and find the correct sequence in which we should proceed, otherwise you will get stuck. So, for the turbine, we are analyzing to get the value of T 04. First we will get the value of T 04s, which is the ideal process. Okay. So, somewhere around here 04s. So, it is the isentropic process. So, we can find T 04s by T 04, sorry T 03 to be equal to P 04 by P 03, which is 1 by R. Okay, remember that T 04s and T 04 both are at pressure P 04, and this is at pressure P 03. Now, is it 1 by R? Is the pressure ratio remaining same as 10, or is it going to be different? Okay. So, it cannot be 1 by R of compressor. So, this is a different pressure ratio, because there are pressure losses. This is 1 by R of turbine multiplied by gamma g now minus 1 by gamma g. So, gamma of the gases. Okay. So, this is in the denominator. So, now first we have to find, then we have another step now needed. We have to find the pressure ratio in the turbine. Okay. So, to find the pressure ratio in the turbine, we should consider the turbine pressure losses. Okay. We should consider the turbine pressure losses. Let us use a different color. So, turbine pressure losses, not turbine pressure losses, the pressure losses before turbine. So, pressure at the exit of the combustion chamber P 02 is 1000 kPa. After the regeneration process, so what is the loss in the regenerator? 2%, 2% of 1000. So, P 05, okay, P 05, the pressure loss between here and here is 2%. So, P 05 is 98% of 1000, which is 980 kPa. I am directly writing, you should write the steps in between. Then there is further 4% pressure loss in the combustion chamber, 4% of the inlet pressure to the combustion chamber. Okay, so, P 03, which is the pressure in the combustion chamber, this is 4% lower. This is 0.96 into P 05. This comes out to be equal to 940.8 kPa. So, this is the pressure at the inlet of the turbine. Now, is this sufficient to calculate the pressure ratio from the turbine? Think for a moment. Is there any other pressure loss? There is another pressure loss, which is at the gas side of the regenerator, but how does it affect the turbine process, because this is after the turbine. So, it affects the turbine process because ultimately the exhaust gases after the regenerator has to go out at the ambient pressure. So, which means that because of losses, the pressure at the inlet of the regenerator has to be slightly higher, which means that turbine outlet pressure P 04 is going to be slightly higher than P 01, okay, needs to be slightly higher than P 01, and that difference is equal to the losses in the regenerator. So, P 04 equal to P 01 plus delta P region B, or region G in this case, gas side, what we have used region G. So, this is equal to 110 kPa, then 100 plus 10. Now, we get the pressure ratio across the turbine RT, which is equal to P 03 by P 04. You can see now that significant reduction in the pressure ratio has occurred. So, instead of 10 now, this is equal to 8.553. Okay. So, this is the pressure ratio across the turbine. What is the effect of this? The net effect of this is that the work output from the turbine gets reduced. So, we get lower efficiency from the cycle. Now, we will come back to this, okay. We will come back to the turbine calculation. RT now we have derived, gamma g is 1.333, okay. Gamma g is 1.333, we have already discussed this. So, this gives us a value of T04S equal to 877.49 Kelvin. So, we have reached this point 04S. Now, we will need to find the point 04. So, the point 04, why do we need to find the point 04 first? Because then only we can find the point T05, okay, or 05. So, 04, for that we will use the isentropic efficiency of the turbine. Okay. So, what is the isentropic efficiency of the turbine? It is defined as, in terms of these parameters, T03 minus T04 by T03 minus T04S. Okay. So, isentropic efficiency of turbine is T03 minus T04 by T03 minus T04S. T03 is known, this is the turbine inlet temperature, which is 1500. We are trying to find T04, T03 again is 1500 and T04S we have already found to be 877.49. Everything is in Kelvin, okay, better to do all calculations in Kelvin. So, this is equal to 0.9, which is the given isentropic efficiency, which gives us a value of T04 of 939.74. Again you can see how the temperature is higher, at the exit of the turbine as compared to the ideal case. Okay. In ideal case it would have been 877.49, but now we are getting a value of 939.74. So, which means that there is less temperature change in the turbine, which also means that the work output from the turbine gets further reduced. Okay. So, now we can go back to the regenerator calculation. So, again going back to the regenerator calculation. We had defined the regenerator effectiveness as T05 minus T04 by minus T02 by T04 minus. Let me draw the diagram again without the pressure losses, because the pressure losses make it somewhat difficult to comprehend, but we can have this diagram as reference. So, without pressure losses it is not difficult to draw. Pressure losses are still there, but we are not drawing those pressure losses here. Okay. Now, this is much better. So, this is from 01 to 02 compression, 02 to 05 regeneration, 05 to 03 conversion, 03 to 04 expansion in the turbine. So, 04 will be higher than 05. So, 04 is equal to 05 dash, and then from 04 to value 06, okay, which is for the regenerator gas side. 0.6 of course has to be higher than 0.2. So, with this for reference, now you can see T05 minus T02 divided by T04 minus T02. So, which means that, so this is given as 95%. So, this means that T05 minus T02 is a known quantity. We have derived T02 610.23. Again remember, all calculations should be done in Kelvin to avoid mistakes. T04 just now we have calculated 939.74 minus 610.23. So, this gives us a value of T05, which is very important because this is the inlet temperature to the combustion chamber. Okay, so, this T05 comes out to be equal to 923.26 Kelvin. So, till now we have found T01, P01, T02, P02, T05, P05 also we have found in the previous slide, it was there. Okay. T03, P03 also is known, and T04, P04. So, all the temperatures up to this 5 are known and all the pressures are known, but still we have some unknowns. We need to calculate the fuel air ratio because that is needed to calculate accurately the work output from the turbine. Okay. So, we need to calculate the fuel air ratio. So, for that we will do combustion chamber calculation. Combustion chamber calculation. We will do the energy balance, and I have done that, we have done that in the previous class. So, to save time I will directly write. So, this is fuel air ratio is equal to, from energy balance, please do the energy balance, CPG T03 minus CPA T05 in this case, okay, because that is the inlet temperature. Exit temperature is T03, inlet temperature is T05 divided by eta B, then QCV calorific value minus Cp of gas into T03. So, the calorific value is given as 45, I think it was already mentioned, or okay, I forgot to mention here. The calorific value is 45 megajoule per kg. Okay. So, CPG is 1.148, okay, CPG remember is 1.148 kilojoule per kg Kelvin, CPA is 1.005, T03 is 1500 Kelvin, T05 we have calculated just now 923.26 Kelvin, and combustion efficiency is given, calorific value is given. So, from all this we get the fuel air ratio to be equal to 0.0187, okay, which is a reasonable value for a practical gas turbine. So, now we can find the net work output from the turbine. Let me use another color to avoid confusion. I will solve it here only. So, what is the net work output? So, net work output from the turbine, this is equal to, so there is no transmission efficiency given, we will assume that transmission efficiency is equal to 1. Turbine work output CPG into 1 plus F into T03 minus T04 minus compressor work input, which is 1, mass flow rate of air is 1, into CPA into T02 minus T01. Everything again is known. So, from this you get the value to be 343.42 kilojoule per kg. So, finally, we get the efficiency eta to be equal to W net by F into calorific value, okay, as defined previously, or net power output by the total energy of the fuel. So, this comes out to be equal to 0.408. So, the efficiency is equal to 0.408. We also want to calculate the specific fuel consumption. Specific fuel consumption is equal to F by W net, if you remember, otherwise derived from the initial value. So, F is known, W net is known. So, this comes out to be equal to 5.45 into 10 to the power minus 5 kg per second per kilowatt. As I was saying, this is a very small value. So, we should convert it to a more practical value, which is kg per hour per kilowatt, which we obtain by multiplying by 3600. So, then we get a value of 0.196. So, 0.196 kg per hour of fuel is required per kilowatt of the power generated. You can of course find the total value. Now, as the net power output is given to be 50 megawatt, we can find the mass flow rate of air m dot A to be equal to net power output by net specific work output, which is W net. Okay. So, 50 megawatt divided by 43.42 kilojoule per kg. This comes out to be equal to 145.59 kg per second. You can try to find out what will be the value of the mass flow rate of fuel. So, these are the important parameters that we needed to obtain. So, W net 343.42 kilojoule per kg. This is the net specific work output. Then thermal efficiency of the cycle 0.408, specific fuel consumption 0.196 kg per hour per kilowatt, and mass flow rate of air that is needed for the entire turbine is 145.59 kg per second. Okay. You should compare the efficiency with the ideal cycle efficiency. For ideal cycle, the efficiency comes out to be equal to 0.614, please verify yourself, ideal regenerative cycle, that this is the efficiency. You can see that there is a very high decrease in the very large decrease in the efficiency because of all these losses and other variations in the means in the real cycle. So, with this we conclude today's class. So, main purpose was to show you. So, there were two things that I wanted to show while or discuss, or there were two purposes of solving this problem. One is of course to learn how to solve design problems like this, or design point calculations, how to do design point calculations, where all these realistic phenomena are present. Second part is to give you a feel of what are the actual numbers which are involved in this type of calculations, what are the scale of say how much power is generated, what is the mass flow rate of air, what is the typical efficiency, what is the typical specific work output. So, you should as engineers you should get a feel for the numbers. So, please pay attention to the numbers also, because these are all realistic numbers. So, you should get an idea about these numbers from this problem. So, these are the references, our textbooks which we are following. So, with this we conclude today's class. Thank you.